Hey everyone, and welcome to this explainer. As your licensed structural engineering tutor, I'm super excited to guide you step by step through a classic, high-stakes masonry veneer shelf angle anchorage question. This is straight out of the CBT NCEES breadth exam playbook. If you've spent literally any time studying for this exam, you know the examiners absolutely love to test your grasp of load paths, equilibrium, and most importantly, your attention to tiny crucial details. So today, we're going to dissect one of these problems from top to bottom, making sure you can walk into exam day with absolute confidence. Let's dive in.
All right, here's our roadmap for today. We'll start with the engineering challenge, move into concepts and governing codes, do a step-by-step solution breakdown, look out for a really common pitfall, wrap up with our final answer and conclusion, and finally, talk about how you can ace the SE exam.
So, Section 1, the engineering challenge.
Imagine the physical reality of the structure for a second. We've got a continuous, rigid steel shelf angle that's supporting a 30-foot-tall brick veneer wall. This angle is secured to the backup structure with expansion anchors. Our final goal here, the exact question we need to answer, is figuring out exactly how far apart we can space our expansion anchors horizontally. We have to support the heavy self-weight of that masonry, and we got to do it without snapping or pulling out those anchors.
Moving into Section 2, Concepts and Governing Codes.
Notice how the exam prompt just feeds you information. It's like a giant puzzle. We have our veneer height at 30 feet, an installed weight of 40 pounds per square foot, and an eccentricity, which is the distance from the backup wall face to the masonry's center of gravity, of 4.5 inches. The anchor sits 5.0 inches up on the vertical leg, and, this is absolutely crucial, the resultant compressive force of the triangular stress block acts 0.5 inches from the bottom. Finally, our allowable tension, or T-allow, is capped at 2.5 kips per anchor. These are the critical given parameters you need to immediately pull from the prompt and organize before doing any math.
And here is the whole ball game, static moment equilibrium. In accordance with the governing design codes, specifically the IBC and TMS 402 for masonry veneer support, we've got to balance the forces. The structural system relies on static moment equilibrium to resist overturning. Basically, if the sum of the moments doesn't equal zero, well, that veneer is coming down.
All right, Section 3, the step-by-step solution breakdown.
We're going to tackle this using a simple four-step methodology to find our equilibrium. First, find the resisting moment arm. Second, define the overturning moment as a function of our unknown spacing. Third, set up our equilibrium equation. And fourth, convert it all to our final exam-ready units.
So step 1 is all about establishing our force couple. The shelf angle resists overturning by pushing against the wall at the bottom and pulling on the anchor at the top. We need to define the true moment arm, which we'll call D. This is the vertical distance between the anchor center line, which is 5.0 inches, minus the centroid of the compression block at the bottom, which is 0.5 inches. So 5.0 minus 0.5 gives us a resisting moment arm of exactly 4.5 inches.
Next up, we define the load as a function of the horizontal spacing, which we'll just call S in feet. Every single anchor is responsible for a tributary width of S. We calculate our total tributary weight by taking that 30-foot height, multiplying it by the 40 pounds per square foot unit weight, and multiplying that by S. That gives us 1,200 times S in pounds. Now, because our allowable tension is given in kips, let's convert that right away. It becomes a tributary weight of 1.2 times S in kips.
Now, take that tributary weight and multiply it by our given 4.5-inch eccentricity. Remember, that's the distance the weight is literally hanging off the wall. This builds our overturning moment formula. So 1.2 kibs multiplied by 4.5 inches equals an overturning moment of 5.4 times 6 inch kips. This is the rotational force that's actively trying to pry the angle off the wall.
Step 3, the magic happens. Let's bring these pieces together to build our ultimate equilibrium equation. Summing the moments about the compression block, we just set the resisting moment equal to the overturning moment. Our resisting moment is our allowable anchor tension, 2.5 kips, multiplied by our moment arm D, which is 4.5 inches. Set that equal to our overturning moment, 5.4 fists. That gives us our core algebraic equation, 2.5 times 4.5 equals 5.4 fists.
Solving that is super straightforward. 2.5 times 4.5 is 11.25. Divide 11.25 by 5.4 and boom, it reveals a maximum horizontal spacing of 2.0833 feet. That right there is the exact mathematical boundary where the anchor tension perfectly hits its 2.5 kip limit.
Now hold on a second. Section 4, beware the common pitfall.
This is where I see 50% of candidates just totally blow it.
The biggest trap is rushing. People will use the raw 5.0-inch anchor position directly as their moment arm. Exam writers put that 5.0 in there specifically to test if you actually understand the mechanics of a force couple. You absolutely must remember to subtract that 0.5-inch compression block offset to find the true 4.5-inch moment arm. If you skip this, your final answer is going to be skewed, and I guarantee you that wrong answer will be sitting right there as option A, B, or D, smiling at you.
And there's another trap right behind it: units. You must convert your tributary weight from pounds per square foot into kips before you equate it to your allowable tension. If you try to balance 1,200 pounds against 2.5 kips without converting, your equilibrium equation is going to be off by a massive factor of 1,000. No way around it. You always have to check that the units on the left side of your equal sign perfectly match the units on the right.
Okay, Section 5, final answer and conclusion.
Let's bring this home. Step 4 is just a straightforward unit conversion. The exam prompt specifically asked for the spacing in inches. So we take our calculated equilibrium spacing of 2.0833 feet, and we just multiply it by 12 inches per foot.
Crunch those numbers, and it perfectly lands us on exactly 25 inches. This confirms that option C is the indisputably correct answer. Not 24, not 32, but exactly 25 inches.
Because here's the truth about mastering the SE exam. It isn't about rote memorization of formulas. It's about seeing how every tiny fraction of an inch actually dictates the physical reality of the load path. A half-inch oversight here isn't just a math error. In the real world, it represents a fundamental misunderstanding of how the shelf angle reacts against the backup structure. Always try to visualize the physical behavior of the structure.
Finally, Section 6, Ace the SE exam. To guarantee you are ready for every single trick, trap, and complex load path the CBT NCEES SE Breadth exam can throw at you, you really need to check out the comprehensive book PE Structural SE Practice Exam Questions. It's available right now from School of SE. It is packed with incredible detailed, step-by-step solutions just like the one we walked through today. Grab your copy, keep grinding out those practice problems, but before you go, I want you to think about something. If that masonry wall had a lateral wind load applied to it simultaneously, how would that fundamentally alter your overturning moment calculation? Think about it, and I'll catch you in the next explainer.